This is a video discussing the basic properties of waves, of transverse waves in this case, for Year 11 physics. So let me draw a wave, transverse wave, something like this. Okay, so transverse waves, if you recall from a previous video, the particles making up the wave, the particles making up the medium oscillate in a perpendicular motion up and down relative to the direction of travel of the wave. Okay, let's call that v, velocity. Let's suppose the wave is moving with some definite speed to the right, in the right direction. That's a transverse wave, so you can think of like little particles. Let's suppose a water wave bobbing along up and down, and they're tracing out this pattern. That's what a wave looks like, a water wave. Dot, dot, dot. Let's call this the x-axis distance, okay, in meters, let's say. Y-axis displacement. Remember, displacement in physics is how far you are from your starting point. Okay, let's call it the origin here, 0. You've got positive displacement up here, negative displacement up here, down here. So what are the parts of a transverse wave? Well, you've got something called the wavelength. That's the distance between two peaks, two crests. Okay, wavelength typically measured in meters. Okay, this is called a crest up here, crest, which is a peak. And the bottom bit, the minimal point on a transverse wave is called a trough. That's a dip. Amplitude, that's how much energy the wave has. That's the height of the wave. Okay, height of the crest or height of the trough, same thing. That's the amplitude. Okay, and the frequency is how many peaks you've got per second. So let's suppose I'm at this point here. Okay, how many peaks are passing through a certain point per second? Let's suppose I'm standing here and I set my timer and I see 2 peaks coming past in a second. The frequency is 2 hertz. And it turns out there's a relationship between the velocity of the wave, how fast it's going, the wavelength, and its frequency. It's very simple. V equals F lambda. V is the velocity, the speed of the wave, meters per second typically. F is the frequency of the wave measured in hertz. Lambda is the wavelength measured in meters. You can use a triangle as well if you have trouble manipulating this. Okay, so F is just V divided by lambda, and lambda is just V divided by F. So it's a very simple relationship. And it turns out as well that there's another relationship between frequency and what's called the period of the wave. Period is the time it takes for the wave to repeat itself. So in this case here, this wave has a period of 2. Okay, for example, 1, to repeat itself. So for it to repeat itself, it's between these 2 regions here. Okay, and I'll show that on the graph later on. But I want to explain why this is the case, why this is called an inverse relation. Inverse, okay? Inverse because if you increase t, the period that's measured in seconds, you decrease f, and vice versa. If you, let's suppose you decrease f, you increase t. Here's why it makes sense. If you decrease t, if you decrease the time it takes for the wave to repeat itself, what you're doing is you're packing in more waves. But if you increase the time it takes for the wave to repeat itself, it's just going to stretch out like this. I'll draw a graph like this. Okay, let's call this time in seconds. Let's call this displacement. Okay, meters. So origin is here. Let's suppose it's 1, 2, 3, 4, 5, dot, dot, dot. And I'll draw something like this as best I can. Something like this. What's the period in this case? Well, the period is the time it takes for the wave, for one wave to repeat itself, okay? In this case, it's 4 seconds. So t is just 4 seconds. Okay, that's the time it takes. So then after this, you'll get this again. That's what that means. It'll repeat itself once more. Okay, that's one wave right here.